Hello, everyone. I am really happy to have our very own Yancy Shirley. Professor Yancy Shirley is a professor here, but I was an undergrad and graduated from University of Arizona, and then you went to University of Texas Austin for PhD, who was with the Evans. And then you came here as a Bob Fellow. And so we had him back, luckily, and then we made him stay here. So faculty. And so we'll hear a fantastic, really interesting story about the Taurus Molecular Cloud. And Yancy?
Yep, and we're going to do a tag team talk today. So I'll introduce grad student Lucy Steffes, who's a second-year grad student here in Arizona, and an undergrad student, Hanga Andras-Letanovszky, who's a senior, is applying for grad schools. For all those of you on Zoom, remember that when we get to that part of the talk. All right. Yeah, I feel like a Tucsonite now. Is that the right word for people from Tucson? I don't know. I've lived here most of my life now, so I think I officially qualify as that. What we're going to talk about today is we're going to talk about core evolution, and most of the studies I'm going to be talking about are happening in this one really interesting region of the Taurus Molecular Cloud called Barnard 10. So a little bit about what we're doing. We're looking at the earliest phases of star formation, what are called starless cores. And I like to think of starless cores as sort of like the basic building blocks of star formation. What I mean by that is a starless core, if it does go on to form a star, is going to form either a single star or a small bound multiple star system. It's not going to form a whole cluster of stars. In order to do that, you would need like a cluster of starless cores. So in that sense, the starless core is like the fundamental unit of star formation. And we want to understand how these things evolve. So here's sort of, you see these typical cartoons that are always put out for star formation. And I think they always give the starless core evolution phase the short shift here. They don't get much. It's always like a little blob. Looks like the plum raisin model. I actually covered it up in this diagram. They were blue like these were, and I made one that was actually probably a little more realistic. Real starless cores exist in molecular clouds which have very filamentary topology. And so they're typically less than about 1/10 of a parsec in size. And at some point, somehow, some of these cores will evolve into something called a prestellar core, which is basically a starless core that's collapsing. And then eventually you will form a protostar, something like the class 0 star formation phase. So what we're going to be following today is this sort of trying to understand how this evolution happens and answering the fundamental question, how do starless cores evolve in filamentary environments? Now, we've been studying this problem for quite a while here at Arizona. I just want to highlight some of the work we've been doing in the nearby Gould Belt cloud. So this is an image here where the sun would be in the center. Here's Taurus, Perseus, Ophiuchus, Aquila, Cepheus. And so there's over a dozen papers here from different members of our research group and also outside people that we've worked closely with over the years. And you'll notice that the vast majority of papers over here on the right-hand side are pointing towards the Taurus Molecular Cloud. And that's because it's so nearby to us, and being in the northern hemisphere, it's up for 10 hours a night, so it's easy to observe with our radio telescopes. So we're going to be focusing mostly on Taurus, and here's sort of 4 views, one in the upper left at optical. You have the far infrared and submillimeter emission from Herschel. It's been mapped in CO, 1 to 0, so we have the molecular gas content. And also here's 90 micron, which is really sensitive to far infrared point sources like embedded protostars that you can see throughout this cloud. But in particular in Taurus, there's sort of like one part of it that we've been doing a lot of our studies, and that's what's called Barnard 10. So if we zoom in to the Herschel image here of the main part of the Taurus Molecular Cloud, you can see up here this sort of like triangle-shaped region that's just below this bright part up here. That's where Barnard 10 is. And what makes it particularly an interesting region to study and a good laboratory for starless core evolution is because there are no embedded protostars in this region. There's one class 2 protostar that's just off the north end. So this is a region that isn't being messed up by outflows, the embedded radiation coming from protostars. It's sort of like a more isolated starless core environment to understand how low mass starless core evolution happens. By the way, all the kind of cores and objects I'm going to be talking about in here, they're all going to be forming red dwarfs, probably M dwarfs. We're not talking about massive star formation. We're talking about low mass star formation and probably lower mass than the mass of our sun in a region like B10. So what I'm going to talk about today is sort of break the talk into 4 parts. And we're going to have some different speakers for different parts of the talk today. So I'm going to start us off talking about the physical structure of starless cores and the boundedness of starless cores. Are they bound or not? And then Lucy Steffes is going to talk a bit about the kinematics of starless cores. And then we're going to finally end up with using chemistry to talk about how we can probe the core evolution history. And that's what Hanga will be talking about in the last part of the talk. So let's start off with the physical structure. So what are the physical structure of starless cores? And so one of the first things that we did, this is over a decade ago, is when the KFPA, which was a 7-pixel camera that worked at 1 centimeter on the 100-meter Green Bank telescope was built. We put in a proposal, Youngmin Sao and myself, who was a graduate student here at University of Arizona at the time, to do the sort of first large-scale mapping of ammonia in nearby molecular clouds. And so this was the first of those maps. It was published in 2015 of the central part spanning 3 degrees of the Taurus Molecular Cloud. And here you can see it mapped in ammonia 1,1 and 2,2, which Youngmin did a lot of analysis for this for his thesis. So this is kind of the beginning of, so I call it the proto-gas project. There was a big project called GAS that mapped all the nearby molecular clouds. And so this is kind of the start of that beginning of that mapping sequence. So within this region, here is Barnard 10 again. Here it is zoomed in terms of the ammonia. And so one of the things that Youngmin did in this survey is he did a dendrogram analysis to understand sort of the hierarchical structure. You have dense starless cores here, but you have them embedded in lower density filamentary structures. So you would like to build up, like, what is that structure? And a dendrogram is a good way for doing that. So using the ammonia 1,1 intensities, this B10 region then broke up into these cores, which we call South 6 through South 17 here. You see all the individual little ammonia cores, and they're embedded within different filaments. You can see at least 3 of the different filaments shown there. Also with ammonia, the great thing you get from using the 1,1 and the 2,2 inversion transitions is it's a thermometer. It can tell you what the gas kinetic temperature is from the ratio of the intensities of those 2 lines. And so if you look at this region, and here's our temperature scale over here, you can see that the vast majority of these filaments are blue down here below 10 Kelvin. It's like sort of about 9.5 Kelvin is the average gas temperature you see along these lines of sight. So they're very cold. These are regions not being heated up by young protostars or anything. They are truly starless. And there's only this one little class 2 protostar up here that's much more evolved up the very end of the region. Now, since you have the gas temperature and you have the line width from your observations, you can decompose the line width of the ammonia observations into a thermal and a non-thermal component. And that's what this is a map of. This is a map of the non-thermal dispersion in the line profile. And from the thermal part, you can calculate for the typical sound speed what the sound speed is in the gas. It's going to be around 0.17 for H2 molecules, the dominant gas component here. And so everything below this in terms of the non-thermal line width would be thermally dominated. And everything above this, sort of like green colors and up to red, the turbulence would be the dominant component in terms of the line width. And you can see that in this region, these entire filaments have already had what's called the transition to coherence. They have thermally dominated line widths for the non-thermal component. Only some of these edges do you start to see this transition into something where you might have turbulence dominate in terms of the line width. So this is a very quiescent, cold region, good region to study where low mass starless core evolution is happening without lots of harassment, which can be important in regions. It's important to study that, like in high mass regions and regions where protostars form. But you also like to have a clean picture where you can separate out all these different effects. And that's one of the reasons why we like this B10 region so much. Okay, so the next thing we did, and this was work that was done by Samantha Shibeli, and she was a graduate student here at U of A, was we took the Aerom 30 meter and the Nika 2 continuum camera at 1 and 2 millimeters, and we mapped this B10 region. And we did this now at 3 times better resolution, 10 arcsecond resolution from the ammonia maps. And the first thing you start to notice is, yeah, you see the same cores here, but sometimes they start to fragment, like South 7.1 turned into size for Shibeli, 7.1 and 7.2. There was another one over here, 13, that fragmented. And so you started to see some substructure even when you went to the higher resolution. But in total, dendrogramming now this continuum map, there's a dozen starless cores in this environment that we can now study the properties of and study their physical structure. So the first thing that Sam did with this data is she did radiative transfer models of the thermal dust emission, okay? And because we had access to a supercomputer here at U of A, we could run large grids of models, varying various parameters in the models, and try to match the observations. So that's what Sam did. She used RadMC3D to do 3D dust continuum modeling. You'll notice, by the way, when you look at sort of the shapes of these cores, these are not little spheres. Some of them are quite elongated. And so right away, we decided we're not going to use binary spheres to try to match the density profiles of these cores. We went straight to Plummer spheres, which are just a more generic version of something that has sort of a flattish plateau in density and then falls off like a power law. So here you see the eta divided by 2 is the power law part of this. And then you can have different semi-major axes. We chose spheroids where two of these were equal and made something easier in the RAD-MCD 3D calculation we're doing. And what we would do is we would simultaneously match both the intensity profile of the millimeter emission and the spectral energy distribution, including all the points observed from Herschel and our millimeter points that we also observed. And when we did the radial profiling, it wasn't just a full azimuthal average. Sam did this very nice trick where she did this in sectors along the major and the minor axes of the core. And so that's what the different shading you see here. So actually, she was actually modeling the profile in both the minor and the major axis direction. And that would help constrain sort of this aspect ratio in the ellipsoid and the spheroid you see here. So she did this running over 1 million models on the HPC. By the way, there's lots of other things you can vary here. Strength of the interstellar radiation field, your dust opacities are also things that can go in as being variables. And so we had a set of different opacities. And you get this as your output. So what you're constraining is the density profile of the core. So this is density versus radius, and this is now thousands of AU that you can see coming out here. So this particular core SAO9, had a density was just about 3 × 10⁵. And you can see that there's a pretty narrow band here. It's actually pretty small. Like we've constrained the density pretty well. That comes from the intensity profile. It's a really good, gives you good constraints on the shape of this profile. And then what the dust continuum calculation is doing is it's self-consistently calculating the dust temperature. And that's over here on the right-hand side of the y-axis. So you can see in the outside of the core, it's about 15 degrees Kelvin, and it's dipping down below 10 Kelvin in the very center because you're shielded from the interstellar radiation field down in the very center of the core. So the dust temperature is self-consistently calculated for your opacity model and drops down like this. By the way, I'll do one little side note. This is one little piece in this paper that I think kind of gets lost a little bit, but I want to highlight this because I just got finished writing a review that's been submitted about thermal dust emission. And so what you see over here on the left is a plot of dust opacity. So this is dust opacity in square centimeters per gram of dust versus wavelengths going all the way from the ultraviolet well into centimeter wavelengths over here on the right. And you notice that for all these different dust opacity models, which these are kind of like the best we have in the literature right now for the diffuse ISM and for dense cores, you can see that they all follow a power law roughly over here in the sort of sub-millimeter, millimeter into the centimeter part of the spectrum. And this is the slope of that power law plotted here into the sub-millimeter. So over here at like 1.2 millimeters, you'll notice that most of these dust opacity models, the dense cores and the diffuse ISM, all kind of scatter around a beta of 1.5 for this power law slope. We were actually able to measure it from the 1 and 2 millimeter observations with a temperature correction for these lines of sight. And so what Sam found was a number that's actually a little higher than this. And it's getting a little bit uncomfortable for me, someone that's worked on opacities now for 25 years. These constraints are not really agreeing very well. The edge of the error bar is just barely overlapping with these models at 1.3 millimeter. We get a beta closer to 2, basically, we find in this region. There's a really cool dust modeling meeting, next month here. And I'm hoping to talk to some people about this particular result while they're here. Okay, so the next question is, are starless cores bound? So we have some idea now what their physical structure, at least some constraints on their density and temperature structure. But the main tool that we want to use for this is the virial theorem, because that's the one main tool that we have in our toolbox, all right? And the virial theorem has lots of terms, and you can ask me about all of these in their gory detail if you want later. But I want to highlight 4 of the terms, but start with 3. So in terms of support terms, we have the internal kinetic energy of the gas in the core. And then in terms of compression terms, there's obviously the gravitational potential energy, but these cores, remember, are embedded within filamentary structures. So you cannot forget the external pressure as well. So this is very, very important that we include this term as well. And you're going to see why. It's because when you make a plot of the compression terms versus the support terms, so that's the y-axis versus the x-axis here, equilibrium is this line right here in the plot, and you give it a little shading here, a little width, because for geometric effects, everything's not a sphere, so you might have variations of factors of 2 and coefficients in these equations. But here are the points for all of the cores from the B10 region. And I want to point out that when we do these calculations, when you calculate things like the gravitational potential, Sam's using the actual profile that she measured, so a 3-dimensional profile. This isn't a projection being turned into a gravitational potential, which has all kinds of biases, as you can show in that calculation. This is actually using the rate of transfer model to calculate the gravitational potential or the density at the outer radius that would go with the pressure that's coming bounding on the outside of the core. And what you'll notice is that, there's kind of broad agreement. There's a few that are below that clearly are not bound, but there's several that look like they might be bound. But when you compare the absolute values of the pressure term with the gravitational potential term, external pressure wins by almost an order of magnitude on median for these cores. So these cores are not massive enough that they're gravitationally bound. They're being confined mostly by the gas pressure in these filaments. And I think that's really important, that these cores appear to be pressure bounded. If you remember, I said there's another term here that we're going to talk about, and that's the infamous boogie person in star formation and all of star formation studies, the magnetic field, all right? And unfortunately, this magnetic energy term is extremely difficult to measure. And in the simplest approximation in the tensor Eulerian version of the Viral theorem, this is basically because a term that looks something like this. It has a volume in it, and it has the B field squared, because you're dealing with magnetic energy, inside minus outside of the core, okay? So what you can do is you can take this term, these B squared terms here, take the square root and turn it into what's called sort of an effective B field difference. And I'll just show that for these cores up here, we would only need about 15 microgauss of B squared difference, basically to bring these back down to equilibrium. That's not much, okay, difference in the B field. So what about the measurements, okay? Well, here they are in Taurus, and they're all over the place, okay? And this is the fundamental problem that we have in star formation. A lot of problems would be solved in star formation if we could just accurately measure B-field strengths, but we cannot. That's the important problem. So here are three different ways of measuring magnetic field strengths using optical near-infrared polarization and submillimeter polarization. These measure the plane of the sky B-field strength. And here is a line of sight measurement using the Zeeman effect on the OH molecule, and you can see there's quite a range in numbers from 25 to 75 microgauss in this study, 13 to 32, and in this one core, an upper limit of 70 could be the maximum amount that you have in SAL 12, and then low numbers for this one line of sight measurement, very hard to do towards this one very dense core in Taurus. And the fundamental problem is that if you have numbers that are spanning, factors of many to almost an order of magnitude here, you have this magnetic energy term going like B squared. And so we have no idea what the effect is, how much support magnetic fields are providing for these cores, at least in a virial sense. So they might be important because this is a small number. It's definitely within that range of measurements. And so you can imagine there are differences on this order, but we just don't know. And it's at this point that I would like to advertise, I think we should just stop using the virial theorem. Until somebody can figure out what's happening in the magnetic field term, I don't think it makes any sense anymore to compare virial energy and gravitational potential energy terms unless you don't know what this support term is doing, and we just don't. So the question is, we don't know how these things are supported if they actually are bounded. But if they are, and the magnetic field is not that important, they're pressure bounded. That would be the dominant term over the gravitational potential energy term for at least these cores in the central part of Taurus. Okay. So this now brings me to the next part, which are what are the kinematics of the starless cores? And so what kind of motions do we see in them? And I'd like to introduce second-year grad student Lucy Steffes, who's going to talk about this aspect of the nature of these starless cores in Taurus.
Okay, yeah, so I'll be talking about some work that I've spent a good chunk of my first year working on. And yeah, we'll be continuing to work on this year. So starting off with another shout out to one of Yancy's former grad students, Brian Svoboda here, built this package called NestFit, which uses a combination of Bayesian analysis and MCMC to get these posterior distributions here, which you can kind of see a little bit better in this bottom one. But what this posterior distribution gives us is a probability of different factors that we're interested in. In this case, in this map, is velocity. And by using a Bayes factor, we can figure out if a 1 or 2 component model is a better fit for this data. The components being the number of velocity components along a line of sight. So for this top posterior distribution that we see, I know it's very small and difficult to see, but the main thing is that there's only a single peak. So there's a 2-component model which peaks the highest, and you end up with these effects over here, these little lumps in the 2-component models. So this one, this pixel, fits very well with a single component model for the velocity. This one down here, though, there's pretty clearly 2 velocity components. one at a slightly redder velocity, and one a little bit bluer. So that helps solve a problem that Young Min was dealing with in 2015, especially in some regions over here that we're not focusing on quite as much in this talk, but will be useful for some of my future analysis in doing additional dendrogramming and figuring out what things are part of the same cores and where the real gas flows are happening to see which parts are actually coherent with each other. So for reference, all of these black X's are those cores that Yancy was talking about. And then we can look here, and all these little green blobs are the different leaves, so those structures within the dendrograms. But for my analysis, I'm interested in looking at how the velocity gradient changes with respect to the larger scale structures, so these filaments. So I started this analysis by using spines. Those were the easiest ones to start finding because they'd already been published by Arzamanian in 2019, which used a code called disperse. The problem with the dust, though, is that dust doesn't have velocity information. So with all of this improved resolution velocity information that we have, which increases our velocity resolution by about a factor of 4, and then knowing from the Bayes factor how many velocity components to expect, the dust was no longer quite good enough because we had so much more information from the gas. So then using the crispy package from Mike Chen, I ran that over this data and specifically looked and compared them with the dust spines that went through, or at least spatially looked like they lined up with the dust spines that went through cores. So I compared the ammonia spines that I got out with the dust spines that went through cores. And then by eye went through and combined them. So sometimes the dust spines were a little bit wider than a single pixel. And for the purposes of the analysis that I'm doing here, I don't care so much about the width of the spines. I'm really focused on like where the main structure of it is. And you'll see why in a second. So then here, by combining by eye, I was able to connect gaps, figure out where multiple things that had been identified to be multiple dust spines, which happened a lot in B10, were actually coherent velocity structures, as pointed out by the gas. And then also fitting together pieces where there were gaps in between spines, either identified by the dust or sometimes by the gas, where I probably need to tweak around with my parameters that I'm inputting into Crispy a little bit more. Eventually, the goal is to use a uniform method and not a combination of the two. But I ended up with these spines here shown in all the different colors. And the reason why I mentioned that I'm only interested in having a single pixel width and not actually how wide these spines are is because I'm turning them into these differential one forms and distance transforms. So in the background map here, we see this distance transform that I made, where I look at the distance, the minimum distance from each pixel to the nearest spine, which then gets color coded here. So you can kind of see where all the spines were with all of the cores laid on top. But then by taking the gradient of this spatially across the entire map, then we get a differential one form, which is a vector field that I will use to then measure another vector field, where we project one vector field onto another and get information about how the velocity gradient is changing with respect to the gradient of these filaments. So an example here. This is one of the cores, SAO6, and up here we see that distance transform in the yellow with the vectors overlaid on top of it, the perpendicular differential one form. Then here is that velocity map zoomed in on SAO 6 with the velocity gradient vectors overlaid on top. So by projecting these vectors onto these vectors, we get a scalar field that is shown here in the purple and green. So the perpendicular velocity gradient. And then we can do the same thing with the parallel differential one form, where all we do is rotate these vectors by 90 degrees to get these ones. And then do the same process where we get this parallel velocity gradient. One problem that I'm currently working on solving is right now, compared to the top and the bottom, or one side and the other side of these spines, the vectors for the differential one form for the parallel are currently anti-parallel to each other. So it ends up producing kind of these false flipping of colors because these vectors are pointing in the opposite direction of these ones. So how does that relate to the cores? One thing that I've been working on is trying to see how this impacts and how this relates to the large scale environment. But because this talk is really focusing on the kinematics and the properties of cores, I wanted to look at how the velocity gradients are changing inside of those cores. So in the purple here, this is where the perpendicular gradient was less than the parallel gradient, so the magnitude of them. And on the bottom in the green, that's where the cores were dominated by a perpendicular gradient relative to the spine that the core resides within. What's interesting here is part of my analysis included looking at rotation, which I'll show some examples of next. But in all of these points, most of all of the cores that seem to be rotating are identified by stars. And 9 out of the 11 rotating cores that I've identified are dominated by parallel gradients rather than perpendicular. So I think that that's interesting here. There are some that I don't think are rotating, though we'll talk about why that might be flawed in a second, that do have parallel gradient dominated motions, and 2 down here that are dominated by perpendicular gradients that are also rotating. But one thing that this suggests is that the cores that are rotating within the spines, not with them. So they're rotating kind of perpendicular to the spines that they're residing within, which should cause some amount of shearing when the core breaks from the spine that it resides within. And speaking of rotation, the way that I did this rotation is first kind of by looking a little bit by eye. So to see where we might have an axis of rotation down the middle with a red to blue gradient going across. And up here you see a few good examples of potential rotation, and on the bottom, some less good examples of potential rotation. But I also fit each of these cores to a plane and used that, the slope of the plane, to figure out the specific angular momentum. And this got kind of tricky to do, not with the angular momentum calculations, but with using the fits of the planes to determine whether or not it was a good example of rotation. Because we see this one, which I had identified as being a bad example of rotation, and it fits very well to a plane. The residuals are below the velocity resolution that we get from the posterior distributions. So by analyzing these residuals, we're not getting any new information, and the planes fit very well. So going back a slide, some of the things that I looked at were some that had a very, very small specific angular momentum, no real axis of rotation. And here, the velocity is almost entirely uniform across the core, again, suggesting that it should have a low specific angular momentum and no real rotation. So with this, looking at the residuals, one thing that we were hoping to do was a principal component analysis. We're not quite sure now if that will work so well because if we assume that rotation is the dominant feature, we're not left with a lot else to look at to see if there's inflows or sloshing or something else going on altogether. But I'm very excited to see where this work will continue for the rest of the semester and my second year.
Cool. And since Lucy has to go to an exam at 1 o'clock, I thought maybe we could take a pause right here in the talk. And if anybody has any specific questions for Lucy about the kinematics analysis, we could do that now. Go ahead.
I understand how the expectation that the velocity gradient would be parallel to the dust fine for the rotating cores. Can you explain
Yeah.
that?
Yeah, so I'll pull up this example. So here the core is sitting within the spine. And if this were a rotating one, if it has a parallel dominating gradient, then we'd see most of the gradient going in this way. So then if it's rotating, it's more rotating this way, like perpendicular to its spine, rather than with the spine, like spinning along inside of the spine like that. So that's the conclusion that I'm finding there. So then
I see. You're not saying that the expectation is naturally that it would be that way. It
Yeah.
just turns out that most of the cases.
yes.
Got it. Thank you.
There's a question online.
Yeah. Megan, would you like to speak up or?
Or we can just.
We can just read it. Megan Harrison to it's amazing work, Lucy. Maybe I missed this, but would the direction and orientation of rotation affect which velocity gradient component would appear as stronger compared to the other?
Can you repeat the question?
So you can actually read it over there?
Yeah, you can.
Yeah.
Oh, okay. Yes, yeah. So kind of similar to Caitlin's question. Yeah, so the way that it's rotating does change that. So with these two cores here, the ones that are dominated more by a perpendicular gradient, but that still do seem to be rotating. So I think at least one of these is an embedded protostar, so it's much smaller spatially. And the larger scale ammonia core, some of it's rotating a lot less, more the inside part is rotating than the larger scale of it, which I think for this one is why you see more of a perpendicular gradient. This one though, yeah, because it's not quite following as much of the same trend as the rest of them, where it seems to be rotating like with some amount of shear inside of the core. That does change how we end up seeing the parallel versus perpendicular component, even though it is probably rotating.
Thank you.
Cool. Well, thank you very much, Lucy.
Thanks.
All right, so one last aspect I want to mention about the kinematics is that something the young man did also in his thesis, and this was in his 2019 paper. He actually mapped this whole region in CCS as well, trying to look at early time versus late time molecules. But actually we put this in the paper, and I'm thinking now this is an advisor mistake. We probably should have made this a separate little paper because it's an interesting result. I think it's been lost in this larger paper. A lot of people in the community don't know that we actually did this. So young man also used the Aero 12 meter to go search for infall signatures towards all of these 39 cores that he'd identified all across the central part of Taurus. And he looked in dense gas tracers that are optically thick, like HCN and HCO plus 1 to 0, to look for a particular line profile, what's called a blue asymmetry. And so you can ask me how that works, and I'll be happy to explain the rate of transfer of that. But what Youngman actually found is that in these cores, infall signatures are very rare. Only 2 out of the 33 starless cores across the whole central part of Taurus had a blue asymmetry, and none of them were in this B10 region, okay? So that doesn't necessarily mean that these cores aren't collapsing. There could be some excitation reasons why we might not see that, but it does seem to be very, very rare seeing these kinds of profiles as well that we see towards the cores. So
Is it the HCN and HCO that plus that the best tracer for the infall, or did I?
it really is. It's the best. You need something that's optically thick so you can see the different layers, the velocity structure. And also something that's very subthermally populated because you need the excitation temperature to be low because you want it to be sensitive to the density increase. You want the excitation temperature to go up towards the center. The gas temperature is actually going down, but the dominant effect, because these lines are so subthermally populated, is the density makes the excitation temperature go up. So you have a positive temperature gradient towards the center of a starless core, and you have something that's optically thick, and that sets up the right conditions to get the blue asymmetry. Yeah. So here's an example of one. This is actually in the hub above B10, and actually young men even use the KFPA to do a small grid of spectra of the HCN. This is the ammonia velocity. You can see that these are blue asymmetric. They're self-absorbed with the blue side line being stronger. So here's an example of one of those two, but pretty rare. So when you add this with what Lucy's got, clear core rotation signatures, kind of hard to see. It's not the majority of the cores, and also infall appears to be very rare. So the kinematic motions are a bit more confused in these regions that are not very, very clear cut in these starless cores. Which brings us to the last part of the talk here, and that is how does the chemistry trace starless core evolution? And there's a lot of things that we could talk about here, but I want to hone in on one aspect of the chemistry in particular, and that is deuteration. This is probably one of my favorite aspects of astrochemistry because it's such, to me, an amazing and cool process that happens chemically in these very, very cold, dense regions. So what is deuteration? Deuteration means replacing hydrogen in a molecule with a deuterium, okay? And if you look in the general ISM, the atomic ratio between deuterium and hydrogen is about 1.5 times 10 to the minus 5. So for every 1 deuterium atom, you'll have 70,000 hydrogen atoms. That's what this ratio tells you. But when you go and observe actual molecules, like for instance, this observation down here in 2017 of triply deuterated ammonia, okay? If you take this ratio and for each one of these, you keep multiplying this abundance ratio, you would expect that the abundance of triply deuterated ammonia to normal ammonia would be 1 part in 10 to the 15, right? But we actually observe it, here it is, at 309.9 gigahertz, and we can measure its abundance, and it's 5 times 10 to the minus 13. It is fractionated by an order of trillion in terms of the magnitude of the abundance, okay, to make this ND3 actually be visible. So this is a very, very strong forward process that happens in cold, dense regions. Now, why does it happen? The fundamental chemistry comes back to this reaction right here, H3+, which is an ion that's formed from cosmic ray ionization of the H2 molecules in the cloud. And so you get to this H3+ molecule, and it can react with HD, and this is a reaction that can go both ways. Sometimes it will exchange that deuterium and make the deuterated version of H3+, H2D+. Other times you can go this way. But this is an exothermic reaction with 230 Kelvin worth of excess energy on the right-hand side. So at room temperature, you can go both ways easily, but at below 20 Kelvin, going back this way becomes more difficult. In addition to that, when you get to these cold temperatures and in these dense regions of starless cores, CO starts to freeze out, and CO, being a very abundant gas phase species, is one of the main ways of destroying H3+ and H2D+. So you deplete the CO, start to freeze out and make ice layers on the dust grains. You get rid of one of the main destruction mechanisms. You're very cold, and so the reaction wants to go to the right, and you start to build up the abundance of H2D+ with respect to H3+. And that's what you see here. These are from models from Ali Sepala of deuteration in starless cores, and these are for H2D+ and even more heavily deuterated versions of that molecule. And you can see on timescales of 100,000 years that their abundance ratios jump up all the way almost up to unity in some cases, all right, in terms of the deuteration ratio. So it's a very, very strong process that can be used to tell you something about how these cores are evolving, their chemical, their evolutionary history. So at this point, I'm going to turn over the next part of the talk to a senior undergrad student at U of A. This is Hanga Andras-Letanovszky, who's been studying these deuterated molecules in B10 for her honors thesis. So take it away, Hanga.
Hi, everyone. So yeah, like Yancy said, I've been working with him for a couple of years on doing an organic deuteration survey of specifically a sample of 11 cores in the B10 region. And I observed specifically formaldehyde and its 2 deuterated forms, HDCO and para-D2CO. And then we also had from Sam Chabelli's work, methanol, and from another firmware student of Yancy's, Hannah Ambrose, one of its deuterated forms, CH2DOH. Now, what's very nice is that we actually had 100% detection rate for all of these molecules in our B10 cores, which ended up being very useful because it meant that I was able to compare the deuterium fractions of these molecules, not just to each other, but also to the physical parameters of these cores that, again, Sam Chabelli had derived from her radiative transfer modeling. So to show the various correlations or lack thereof that I found, I am using what's called a graph here. And basically the way this works is each node is a different quantity, and then the distances or the edges between these nodes were weighted using what's called the Spearman rank correlation coefficient, which is just a way of measuring how well correlated two quantities are. And they were weighted in such a way that the very well correlated quantities, like for example, HDCO over H2CO and parity 2C over H2CO, are very close together. But much less correlated quantities, like for example, HDCO and the HDCO deuterium fraction and the central density Yancy, are a lot further away from each other. And you can see an example of what that looks like here. This is the plot of the actual data points, and yeah, not really a lot of correlation happening. But what's interesting is you can see that there's across the board a general lack of correlation between these deuterium fractions and these various physical parameters, especially the ones that trace evolution, like central density, which is very interesting because it means that we are getting unique information about how these cores are evolving just from their deuterium fractions. And I'll get to what that is in a moment, but for a second, I wanted to talk a little bit more about these Spearman rank correlation coefficients because they have two major flaws that I wanted to try to address. The big one is you'll notice that, well, the actual data has uncertainties and the Spearman rank correlation coefficient doesn't inherently account for that. And the other one is that given that we're looking at a fairly small region of Taurus, our sample size is pretty small. So to try to account for these two different issues, I used two different methods to get a sort of uncertainty in these Spearman rank correlation coefficients. For the first one, which was the uncertainty due to the uncertainty inherent to the data, I used a Monte Carlo method where I essentially for each data point made a probability distribution function based off of its uncertainties. And then I pulled from all of these different probability distribution functions to make a plausible data set that you could feasibly get with those uncertainties. And then I did that like 10,000 times, and each time I calculated the Spearman rank correlation coefficient, resulting in this distribution you see here. And then to deal with these uncertainty due to the small sample size, I used what's called jackknife resampling, where I essentially just one at a time removed each of the different cores from my sample, and then each time recalculated the Spearman rank correlation coefficient, which resulted in another distribution you can see here. And what's very nice is that in both cases, you can see that the median value, which is this orange line, is almost right on top of the actual Spearman rank correlation coefficient we got just from our data, which is pretty great. And although both distributions are kind of wide, you can see that in general, we're still getting that no matter what, this is a pretty poor correlation. So this reinforces that these Spearman rank correlation coefficients are a robust way of measuring these correlations. Now, going back to what I said about these deuterium fractions tracing an important aspect of these pores evolution that we don't get from the physical parameters, I wanted to talk a little bit about the actual rate of the evolution. So what you're seeing here is a couple of example tracks from a series of StarForge and HD simulations of core evolution that Stella Offner and her team at University of Texas at Austin did. And you can see that you can have cores that evolve very, very quickly, where the density almost immediately skyrockets and the core collapses into a protostar. But there are also a lot that take a lot slower and more meandering of a path. And you can even see that for some of these very slowly evolving cores, the density kind of bounces around a bit before it finally shoots up and the core collapses into a protostar. And what we think is that these deuterium fractions could help us figure out whether a core is evolving very quickly or very slowly. And to illustrate why, I want you to consider for a moment two hypothetical starless cores that are at the same point in their physical evolution. Say one of them, specifically they have the same central density. But one of them has a lot higher of a deuterium fraction than the other. Now, the thing about deuterium is that, like Yancy talked about a little bit, it builds up very slowly in cores over time. And because of that, the core that has the much higher deuterium fraction probably took a lot longer to get to the point it's at its physical evolution than the one with the much lower deuterium fraction, because it's had this time to build up all of these deuterated molecules. And what's interesting is that if we apply this logic to our sample of cores in B10, we get a very interesting spatial correlation, actually. So this here is zoomed in on the B10 region, the maximum likelihood velocity of the ammonia in the region, which Lucy had talked about a little bit. And we also have some of her dust spines overlaid in white. And this is all just to show which of these cores are in these kinematically coherent filaments. Like, for example, we've got this northern filament up here, this southeastern one here, and the southwestern one here, and then 10 and 15 are just kind of hanging out on their own. But I overplotted in these gray circles, which the size of them, it corresponds to the HDCO over H2CO deuterium fraction. And what's very interesting is that you can see that this northern filament up here tends to have much higher deuterium fractions than this little southeastern filament here. And same here, much higher deuterium fractions in this filament than that filament. And that's pretty interesting, especially because you may be thinking, oh, well, maybe it's just that all of these cores are super dense and these ones are a lot less dense. But that's really not the case, because if you look at this same graph for the central density, it is completely all over the place. Even with the same filament, you have like a factor of an order of magnitude difference in these central densities. So what we think this is showing is that as a whole, these filaments are evolving at different rates from each other, which is pretty exciting because it's pretty cool. At least I think so. How are we doing on time?
Yeah, time, go ahead.
Okay. Another result I also wanted to highlight very quickly, focusing more on just the chemistry itself, is how it is to do with the inheritance of these molecules. So what this graph is here is it's a plot of my sample of cores here and their deuterium fractions in D2CO over HDCO, D2CO over H2CO, and then HDCO over H2CO, as compared to a sample of other starless cores from literature, as well as a bunch of literature values for protostellar cores and even a couple protoplanetary disks. And these red dashed lines here are the median values of these deuterium fractions for each of these little boxes. And what's really interesting is that you can see, especially for the D2CO to H2CO ratio, this median is remarkably constant across these different evolutionary stages, which could be pretty compelling evidence for these molecules being inherited across these various evolutionary stages. And one particularly interesting example is the class 1 protostar IRS-63, which was studied by Linda Podillo et al. Last year. And what they were finding is that the pair D2CO is tracing this little region here where the protostar streamer is impacting the surrounding disk. And that's pretty interesting because what's probably happened is this shock is releasing this D2CO from where it froze out onto these icy dust grains. And well, that D2CO had to come from somewhere. And that somewhere we're thinking might be all the way back in these starless cores. So yeah, in conclusion, the chemistry is important. You should pay attention to it. Yeah.
Thank you, Hanga. Okay, so to sort of summarize everything together then, we've done a lot of work over the last sort of decade in this region. We found out a lot of things about how core evolution happens, but there's still a lot more to learn. So the B10 starless cores, if they are bounded, they're pressure bounded, but B fields, you got to be careful about this. And I think they're a real problem for doing virial analysis, and people always ignore them because they don't know what to do with them. And it's a mistake because it means you don't know what's actually going on if you're doing that. These cores are not in hydrostatic equilibrium. They're not spherical structures, but 3D modeling has constrained their density and temperature structures. We use generalized Plummer spheroids to do that. The velocity gradient analysis that Lucy showed really has no preference for parallel versus perpendicular. Maybe the rotating cores have a slight preference towards more of the parallel motions, but in general, they're pretty large error bars, and the motions are kind of complicated. It's almost like the turbulent velocity structure. Even though the cores now, that turbulence is dissipated, like the velocity vectors might still be kind of randomized in some way. And so it's like there's no strong velocity motions that you're seeing in these cores. Most cores do not have even clear rotation signatures, and core infall signatures are also very rare. The work that Hanga has shown is that the deuteration is a good probe of dynamical history. I can tell you about maybe the relative rates at which cores are evolving in these different regions. And we see some nice evidence for some potentially differential, even filament scale evolution from those deuterium rates. And this is something that another undergrad student had just started a space grant project here that I'll point out. Grace Kaiser, who's a sophomore, is now going to try to test this hypothesis by looking at some more cores and filaments in these same molecules. But I think at the end of the day, if I have to sum up like all of this, like what's really important for core evolution, environment seems to matter. The environment, like things like this tell you that. And where your core is helps drive the evolution of what's that core, because you have things like maybe being pressure bounded by what's happening in the outside. So you can't just study the core itself. You have to understand the environment around. That's what things like what Lucy's doing with the larger scale kinematics in the filaments is also going to address. So I think at this point, we'll stop for questions. And if you have any questions about the chemistry, Hanga will answer it. And anything else, I'll try to answer it to the best of my ability. So thank you very much.
Thank you. Yeah.
Very, but actually have a question about you have two filaments and you have different duration. Do you know like these two filaments have different, you have to measure the different ionization maybe in these filaments?
We don't, yeah, you want me to take that one or do you want it? Okay, so, yeah, we haven't talked much about that. It's really hard to measure. You could try to do things like H13CO plus, like the DCO plus ions are one way of, but they're very uncertain in terms of measuring the ionization fraction. To my knowledge, nobody has done that yet. It's not published it in these regions. It's something we could maybe look into to see if there's different ionization fractions. And that can affect your rate, right, at which the duration happens, because it's the cosmic ray ionization that's making the H3 plus, like in the first place, right? But can this explain our variation that we see sort of factor of 2 difference? I don't know off the top of my head, but I think what we could do is we've been talking with Ollie Seepla, which we did in Garching when we were there for a meeting at ESO in March, last spring break. And, you know, we could ask that group, we could try running some models where we have that as just an axis where we're varying the cosmic ray ionization rate, see how different the rates are building up to the levels that we see basically in these cores. It's a complicated problem though, small. And this is what, Hanga, maybe you can say a very brief word about what you're planning to do for your NSF graduate research fellowship.
For my graduate research fellowship, I'm writing a proposal to work with Ted Bergen over at the University of Michigan to basically do a bunch of chemical simulations paired with MHD simulations to see how these different evolutionary tracks how different evolutionary tracks can result in different deuterium fractions, to test what I was talking about with the them tracing the dynamical history of the cores. And the cosmic ray ionization rate is one of the various initial conditions we would be varying, along with the actual specific evolutionary track it would be taking for the density. So yeah, hopefully if I get into the University of Michigan and work on that project with him, hopefully that could answer some of that as well. But I have to actually get in first.
So I want to come back to this velocity question. So you mentioned that, you know, most cores don't show rotation, and that's like somebody who does the sort of simulations. I'm like, great, it seems like, you know, that shouldn't be, it's not obvious why that would be true. I'm wondering whether or not the results still follow the line with size relation, and whether or not you can derive, you know, you can still measure a net angular momentum vector, right? So in a numerical model, you could measure a net angular momentum vector, and you could show that it's still consistent with forming a disk that's 100 AUE, even though there's no net rotation.
Yeah.
So how much of that can we do with this data set?
Yeah, so
much higher resolution.
I'll answer for Lucy a little bit. Some of the things I've seen that she's done so far in her analysis, right? So she has made a J over M over versus R plot for the ammonia data. There's other dense gas tracers. So you can compare ammonia to N2H plus, for instance, and they agree. They correlate the J over M versus R for these cores. But she also took some of the cores that don't have strong rotation signatures, or it's probably not a rotation signature, and still fits a plane and calculates J over M versus R, and it still looks like it correlates. It's a little scary because you just kind of get that correlation naturally, right, out of the observations of the way you're doing this plane fitting. So that's a little bit of a question I have about, you know, the people that have done this fitting in the past. So Chris might have a comment about this. So yeah.
Because I'm measuring with my simulations, and then I have Lucy's data with this, and then they all fit.
Yeah.
And that's what.
But I mean, that's well, I don't understand why this is so shocking if it's just following. Basically, you're saying that the relative velocities from turbulent flows increase as a function of length scale.
Yeah,
Length scale math is tracking the length scale as well. And so if your net angular momentum is just a cancellation of two random velocities, that should still go, whatever you get in excess should still go up with mass and therefore distance. It seems okay to me.
yeah, it could be, that could be what the explanation is for why it's behaving the way it is, but I'm a little dubious about it. I mean, there's lots of different things. I asked Chris about this actually at an internal symposium talk a year ago, right? The thing that all of us observers do, because we don't know how to do differential fits to the rotation in these cores to calculate a more accurate J of rim, is we fit a plane and we assume solid body rotation, right? Well, if you have something that doesn't look like rotational, you're fitting a plane and assuming solid body rotation in the math, you've inherently baked in an assumption that is just wrong, right? And so like, are you calculating a J over M that is meaningful in any way at that point? And so that was the exact question I was asking Chris a year ago about that. So yeah, I think this is all fascinating, but we should talk more about this, Caitlin, for sure.
Like, you haven't checked what the,
Yeah, if it's, so what we did is she had the points, there was a Jaime Pineda and there's a Chin paper also from a couple of years ago that had the J over M versus R goes like R roughly to the 1.5, right? All these literature points, including even high mass, you have this like, you have to be really careful. There's a really disparate set of observations that come from different techniques, different resolutions, different kinds of objects, but it spans over a wide range of radii. And the ammonia stuff is kind of down in a little clump down here, but it does like, it's not disparate away from what I saw. I don't think it was far away from the X relationship. So this is something she's just been working on actually the last couple of weeks. So we were also looking at like, if you take the average, the gradient vector directions, like calculate like an average vector for all of those, like which direction point as they compare to other gas tracers. And so she's been working on an aspect of the analysis that looks at things like that as well. But yeah, we should wait until we get the final plot because there's some things we still are sorting out on this. So I want to be a little careful about what I'm saying about that. And it's our own reason why we didn't show it because we've just been doing this most recently. So yeah.
So we got the,
Oh, wait,
Was there? Yeah.
one has a question.
Hey, Al. All right. Should we read the question? Yeah.
Yeah.
So two paths to deuteration have different independence, rise from a chillier path than HDCO, for which CH2D plus may be involved. Do you see evidence for the two paths in your data? So maybe, do you want to talk about, actually, there's the ice versus gas. Where are we going? I'll just say real quick, Al, the CH2D plus, I think that the temperature is too high for anything we're seeing in these cores, because that's usually like temperatures of like, I think it's 50 Kelvin and above, typically for that ionization route to be important for the, so these cores I think would be too cold. It has to be through H2D plus,
But
but
these are much colder than that. right?
yeah, maybe I can bring up that slide. You can talk real quick about the column densities somewhere here, any extra slides. Let me find it. Sorry, we have a lot of extra slides. Yeah, I think it's that one, right?
Yes,
Yeah,
that's
okay.
the one. Yeah, so we were actually finding some evidence for the different deuteration pathways. So gas phase versus grain surface for specifically the two deuterated forms of formaldehyde, because we know CH2DOH that correlates, I think, almost exclusively on the grain surface. So, and I know for a while we thought that was the same, that was the case for HDCO and D2CO as well, but they really don't correlate with the CH2DOH at all, pretty much. So that's indicating that there's probably more like a pretty significant gas phase component for both the HDCO and D2CO. But what's interesting is then the D2CO correlates very well with a couple of these dense gas tracers we have, like N2H plus and the parammonia. So what we're thinking could be happening is maybe it's mostly gas phase for D2CO and potentially it's more of an even mix almost for HDCO, but yeah, we aren't like 100% sure, obviously, but that could be what's happening here potentially. So, yeah.
Okay, thanks.
Thanks, Al. It's good to hear from you.
So in your summary slide, you mentioned about environment matters. So what type of what kind of possibility of environment, what could that
Yeah,
be?
I think in general, that's got to be true for star formation because you have difference between low mass and high mass star formation. So ignoring that, even within a low mass star formation environment like that. So what's fundamentally driving the difference in evolution rates? If this hypothesis is true, and we have these two filaments and the cores have all ranged kind of like a similar range in densities, but they're all over the place for the individual cores, right? Then you have one filament that has dynamically got there pretty quickly to this state, and the other one is taking longer. Why? What is it that causes that to be the case? I suspect it has to do with what the magnetic field strength is doing and how much support it's providing within the filament that's driving the rate at which this evolution is happening. That's what I think might be one of the answers for this. And that would be the case that you just have different field strengths on average between those two filaments. Schwo pointed to maybe it's something that in the deuterium chemistry could be the cosmic ray ionization rate. I don't know why that would be so different, like less than, it's basically the whole thing spans 0.3 of a parsec too. So this is one idea of when we do these chemical studies in this region. If you have a whole heterogeneous sample of cores, that tells you interesting things chemically about average effects over entire populations, right? But when you're looking at a population like this, you would think the initial chemical conditions must be relatively similar, I would think, between those different varieties, even though they have different, maybe dynamical rates of evolution in those regions. And so, yeah, I think at the end of the day, those are the kinds of things. It's probably like the larger scale structure. What is the pressure in the filament? What is the magnetic field and how that's controlling the evolution? I think those are the things for these like low mass regions that are probably controlling the evolution of these cores within this. Yeah, Remount.
Yeah, it's very interesting to see all this chemical evolution in quiescent clouds, basically. But at the same time, listening to your talk, it doesn't sound like any of these clouds is on a clear path to star formation, right? And so does this point to the fact that there's actually a good chance that there will be no stars coming out of this, and that on
Yep, we don't know for sure, but let me just point out, Taurus is forming stars, right? So there are stars, and this is the B213 region. B10's up here, okay, where there's no things. Here's B7, which was that collapsing region I showed you with the infall signature, right? These are the protostars down here in the west side of B213, and then there's somewhere on the east side. This is B218 here. This is B217. These are down in B18, not 218, but B18. This is over in Hylas Cloud 2. L1521 is one of these class zeros over here. And there's a lot of star formation that's happening embedded. So, but I'll go back to your question. I think it's a question I've been asking. It's like, do we know what these things are going to do? And the answer is we don't, because we don't know whether they're even bound or not, right? And so, but I would be shocked if none of these, I would put my money that if none of these ever went on to form a star, right?
No, my question,
Sorry,
you have the statistics by looking at the cores versus the number of ones that you see. So do you have kind of a rough idea about now 1 out of 10, 1 out of 100, or?
Yeah, I took out a whole bunch of stuff about lifetime here, right? Just to make our time limit. And so there's some interesting things you can do with like counting statistics, okay, in terms of the course. The counting statistics works that's been done before, and one of the reasons why I took it out of the talk is I think that there's a flaw in the way it's been done, and it messes up how you interpret the counting statistics. So what I'm talking about is the Philippe André and group have done with the Herschel Gould Belt, they've mapped all the nearby Gould Belt clouds. They've identified hundreds of starless cores in each cloud, and then they have a criteria. They use a Barnard-Ebert criteria to determine whether or not the core is prestellar or starless, meaning gravitationally bound or not. And a few of these in these regions here, they will say it's gravitationally bound, and I think they're pressure bound if you actually do it more carefully, right? So that's an issue. But also, so then you're counting this wonky criteria, this little hand wavy about whether something is prestellar. And I count up the prestellar cores and then compare them to the number of cores. So if you think those are the ones that are most likely to go on, then you can do counting statistics and get like a lifetime for those phases for when you're a prestellar core at a density of 10 to the 5 or 10 to the 6. And that's the plots you see in like the annual review articles from a decade ago, right? The problem is are those really prestellar cores, right? Like that's number one. So are you mixing and matching cores of different types in there? And so that messes up your counting statistics, and therefore those lifetime markers. But then the second aspect, if you look at that, is you look at some of the recent simulations, the MHD simulations coming from people like Stella Offner that have traced core evolution over time in their fit. You'll see cores that at some point looks like it's bound, and then something happens and it becomes unbound, it flies apart, and it becomes a stochastic process where you have some probability, like the things that are low density starless cores, the probability that's going to turn into protostar on average is lowish, right? And even something that looks like it's really bound and very dense, it has a much higher probability, but it's not 100%, right? It could still dissipate and something could happen to it. So there may be some degree of stochasticity to all of this at the end of the day as well. Yeah.
This maybe a similar question. What if you say, let's not worry about understanding an individual core? Let's just ask the question, if I take Taurus, and I say it should have the same star formation efficiency as like a galaxy. I could count up all the things that are in stars or protostars. And then I could count up all the rest of the gas and say, how much more of Taurus needs to turn into stars before I reach the threshold that I've satisfied star formation efficiency with this planet.
Yeah, it'd be interesting to try that
Yeah,
calculation.
not
Yeah,
been done,
yeah,
but
so-
interesting, good.
I was going along the same lines. It almost sounds like, this is such a quiescent region. It's completely divorced from the complete IMF, right? Where you have like high mass star formation and somehow there's some rule that tells you this.
But you're never gonna form it up. Wait, I don't know.
The highest member here is A star.
Yeah,
Yeah.
but that's fine, but you just say, I'm just saying, like, take the total integrated mass and do an efficiency calculation, because that is presumably not off by factors of,
Yeah,
orders of
let's see that.
magnitude.
And you can do even better because you can measure how much dense gas mass, you don't even have to use the total, right? You can use the relation based on things above 80 of 8 magnitudes, right? Yeah.
Then you could just ask, okay, if I'm looking at something without a star in it, like what fraction of those need to go on to form stars, given all, like, you have to make
That's right.
you have to do a lifetime of the molecular cloud, but I don't think that's so bad.
But you can also assume, the main assumption you have to make in that case, I've done part of this before, because I did this for one of these NGVLA conferences back in 2018 in Portland. If you look at when the Herschel results are coming out, and you look at the total number, like their clump mass distribution, core mass distributions, right? You get like in this part of Taurus, like right in here, they're finding several over 500 cores, right? You look at the number of protostars, and then you count up how many are class 2, you think that'll have a certain lifetime. There's no way all of those things are going to turn into protostars unless the star formation rate is going up,
Right.
increasing very rapidly, right? So the vast majority of those cores are being identified just as general starless, and the Herschel catalogs have to be transient, right? So it's part of the talk I took out, right? Okay, and so that's true. And then do you believe they're prestellar criteria, right? And then that gives you lifetime estimates, which are longer than free fall by factors of a few. So something may be holding them up, but the question of whether or not you really can count them as prestellar, and yes, those are going to go on to form stars is in question, in my opinion. So it's difficult, but I think there's ways around it. We should talk more about this, Caitlin, of like attacking this argument to see if we can do something with the number statistics now. Yeah, I think it's all fascinating question. But yeah.
Just
Yeah, thank you very much.
Thanks for, Hanga and also Lucy not here, not Yancy. And they are here in store, so feel free to stop by and ask more questions. Thank you.